if I have, say, 20 points in a data set, and I think about I then running from 1, 2, 3 up to 20, and I think about computing values of I minus 0.5 over n, I minus 0.5 over 20 in this case. 1 minus 0.5 over 20 is 0.025. 2 minus 0.5 over 20 is 0.075. 3 minus 0.5 over 20 is 0.125. And then down here at the end, this is 0.975. The point is going to be then that the I minus 0.5 over 20 quantile of the data set is going to be, in this first case, the first smallest value. This is going to be the second smallest value, the third smallest value, and this is the largest value. And what I've just given you is an admittedly arbitrary but somewhat attractive convention that says, well, each data point is 1/20th of the data set. 1/20th is 0.05. The difference between these successive values here are exactly 0.05, and I'm just going to say that the smallest value is the 2.5% point of the data set. The second smallest value is the 7.5% of the data, 7.5% point of the data set. The third smallest value is the 12.5% point of the data set, and so on. So with that convention, okay, with the convention that says that we're going to agree to call the ith smallest value in the data set the I minus 0.5 over n quantile, the way that we make a normal plot, so is by plotting ordered pairs that have this form. For a horizontal plotting position, we're going to use the I minus 0.5 over n quantile of the data set. And for the vertical plotting position, we're going to use the I minus 0.5 over n quantile of the standard normal distribution. And so the textbook writes something like this. It writes, say, Q for the data set, I minus 0.5 over n. Okay, that's standing for the I minus 0.5 over n point of the data set, and then Q sub z, that is the I minus 0.5 point of the standard normal distribution. And in fact, by convention, that guy is the ith ordered x value, and so it's something like this. Okay, and as a matter of fact, this thing is what's read on the margin of a standard normal table from a value in the body of the table that's I minus 0.5 over n. So this is a z value corresponding to cumulative probability I minus 0.5 over n. So for example, there is a data set in the textbook on page 208 that is, so this is from page 208 of the textbook, that is 20 measured thicknesses of some tongue pieces on some machine levers. So there are 20 measured thicknesses, the smallest of which is 0.1807, the next smallest of which is 0.1811, and so on, the largest of which is 0.1868, and as I remember, these are in units of inches. I believe that's correct. Okay, so what am I talking about doing here? Well, I'm talking about making up ordered pairs and plotting them, the first of which is the smallest data value. That's the horizontal plotting position, and for a vertical plotting position, what I'll use is a z value that corresponds to a cumulative standard normal probability of 0.025. That is minus 1.96. So this is z corresponding to 0.025 cumulative standard normal probability. That's the first point I'm going to plot. The second point I'm going to plot has a horizontal plotting position of 0.1811, and the vertical plotting position is going to be minus 1.44. And the news here is that this point is the z not corresponding to 0.025, but z corresponding to 0.075, etc. Okay, and I'm going to make a plot of 20 plotted ordered pairs. Now, the way to do that most easily, of course, is to not do that by hand, but rather to use a statistical package to do that. And so here's what you would do in JUMP in order to make a normal plot for these tongue thickness data. So there's a data table with the tongue thickness data in it, and I'll come up here under the Analyze menu, and we will analyze distribution, and we'll analyze tongue thickness, and here's what we get to begin with here. Let's use a horizontal layout for this JUMP report. Let's get rid of this outlier box plot, and here is a is a histogram of those tongue thickness data. Just looking at that histogram, you can see that that distribution is long tail right. It looks like it's skewed right. So I expect when I do normal plotting of this data set to see something in the plot that corresponds to that right skewness. Now here's how in JMP I go about making a normal plot. I can come to this tongue thickness red triangle and come down here, fit distribution, and fit a normal distribution. Now what that's produced is, for one thing, this is a normal probability density that has been superimposed on this histogram. It's a normal probability density with mean 0.18246 and a standard deviation of 0.0014. So I can already get some sense as to how this normal curve is describing this histogram, and the fit is not great. If I come over here to look at the fitted normal, well, here is your estimate of mu, that's x bar. Here's your estimate of sigma, that's s. That's the mean and the standard deviation that you're used to seeing over in this part of the report. I should mention very briefly here that JMP uses a slightly different convention for quantiles than this I-0.5 over n business, and so if you have some difficulty getting your understanding of quantiles to match up exactly to what JMP puts out here in its report, that's because they've made a different arbitrary convention than the one that the text and we're going to use in IE361. So if I come up here now to the fitted normal and say I'd like to see a quote-unquote quantile plot, that's what JMP calls its normal plot, and here it is. It's got some extra stuff on here that I just assumed weren't there, so I'm going to pull out, turn off the quote-unquote confidence limits. I'm going to turn off the quote-unquote line of fit, and I'm going to turn on probability labels for purposes of helping us think about what's being plotted here. Now, what we've got is a mostly straight line plot. That is, if we look at those points on this normal plot, look back over here on the histogram. Those plotted points correspond to these values of tongue thickness that are the smaller values of the tongue thickness. And you could imagine laying a fat pencil, if you will, on over the top of those points and having that fat pencil cover that. That is, this plot is reasonably straight line. That suggests that, well, this part of this distribution over here is, well, not terribly, it doesn't fail terribly to be bell-shaped, but this point over here is a different matter. Okay, so let's grab that point. That's coming from this single large observation. And the point here is that even if I could think of these points as producing a reasonably straight line plot, this one over here does not fall on the same line as the rest of these. I would have to take this point and move it fairly radically back to the left in order to make it get in line with the others. On this picture, I would have to take this bar and move its probability back to the left if I wanted to make this histogram look more bell-shaped. So the point here is that here's a normal plot. These are z-values on this axis. If I wanted to use an axis over here that give probabilities corresponding to those z-values, we were able to add that by using these probability labels on the jump normal plot or quantile plot option, and that's a very automatic, quick way to make a normal plot, and it shows us pretty definitively that although this might be considered fairly straight line, and therefore this distribution over here not terribly failing to be bell-shaped, these, or this point right here, this single largest value in the data set corresponding to this plotted point over here, clearly destroys the bell shape of the distribution, and this point would have to be pulled back to the left. This bar would have to be moved in back to the left in order to make that distribution look normal. Okay, so that's how we make a normal plot.